Here. Some great questions though in the other class. It did delay us a little bit, but there were some really intriguing questions because this is kind of one of those topics where we're going to begin to really talk about some heavily theoretical stuff. For example, like the speed of light and the concept that it's a finite amount and that you can't supersede it. A lot of theory involved, and like by theory I mean a lot of stuff that isn't necessarily or has not necessarily been proven yet, but theoretical stuff that we're looking at. I didn't. Today?
I've only been to like 3 places. All right, thanks.
All right, I'll keep my eye open. All right, anyhow, so we're going to do a decent amount of stuff with this section. It really is a continuation.
I heard like theoretically you go fast and speed of light, you go back in time.
Yeah, so last class we had a whole idea of what does it mean to time travel. And it's a difficult concept to understand, but to give you a quick idea, a simple example would be to think back to earlier this year. Do you remember these graphs, position versus time? Earlier in the year we did graphs with these and we said, all right, you know what? If the position is going up as time goes on, we said the person had a positive velocity, it was the slope. And then if the position was going down, we said the person had a negative velocity. If the person's position was not changing, we said that the velocity was equal to 0 for that. Well, those are the 3 scenarios we looked at, because those are the 3 only physical real scenarios. Either you're standing still, going forward, or going back. Linearly, we're talking about. Now, the idea of time travel and going fast in the speed of light is really where this comes into play. So imagine if I were able to move from here to there in 0 time. No time elapses, yet I can move from here to here. There's a term for that. What's the term for that? When you can move from one place to another with no time. Yeah, teleportation, or some people call it instantaneous transmission. Meaning your body, your molecules can literally be in this place and in that place at the same instant in time. That's really what time travel is. It's a little bit more than that, but here's the idea. If I could go from a position, I'll use blue. If I can go from a position to start, say I started at a position of like 2 meters, and no time elapses at all, and I go to 10 meters up here, well, my graph would look like this. It would be a vertical line. Again, I started at a distance of 2 meters from the origin, and then I ended up at 10 meters from the origin or some other distance, but no time elapsed. That's what the graph would look like. Now, the interesting part is to recognize what's the slope of an infinite line. What's the slope of a vertical line? 0 is the horizontal line. Horizontal line, the slope is 0. Remember, these are slopes. Positive slope, 0 slope, negative slope. What's the slope in math that you learned about a vertical line? You call it undefined, right? That was the term, undefined. Now, to give you a little preview of pre-calculus and limits, and if you go on to take calculus, undefined is just a way to say we don't know, but it's not definable. But in reality, you could say the limit is definable. And the way you look at this is by approximating, and if you think about this for a second, you approximate, well, what's slope? Slope is the change in the vertical component, which in this case would be 8. We go from like 2 meters to 10 meters, over the change in the horizontal component. But if no time has elapsed, the change in time is just 0. So you end up getting 8 over 0, which you all have talked about as undefined. Undefined, that's what that phrase means. Well, in reality, if you divide something by 0, 0 can go into 8 infinitely many times. That's what division is, right? If you think about 8 divided by 2, you say, how many times does 2 go into 8? It goes in 4 times, right? Well, how many times can I take 0 and put it into 8? I can do it all day long. Am I ever going to fill up 8? No. It's like filling up a basket that has spots for 40 objects, and you have 5 at a time. 5, 5, 5. You do it 8 times, and you get to 40, right? You're done. But if I take 0 objects and keep putting 0 objects in a box that can hold 40 objects, am I ever going to fill the box? No. That's what division by 0 is. It's saying that this will go on forever. So theoretically, this is where the theory comes in, this is what we call a limit. It's approximately infinity. So what happens really here is that if I'm able to go from here to here in no time, my velocity would be infinity. And you can't have a velocity of infinity. That's pretty much what time travel is getting at. Because of the fact, and let's go to the next slide, and the next one we're going to see it, we're going to talk about the speed of light. The speed of light is a value that cannot be exceeded. If you could exceed the speed of light, you would technically be able to time travel. Your body would also be distorted. You wouldn't age the same way. If this interests you at all, please do a little more research. This is, again, these sections are, remember I talked about how it's like the tip of the iceberg. There's so much more. If you want to really theorize or think about this a little more, read Einstein's Relativity. It's not a heavy math book. It really isn't. It's a lot of theory. It's like maybe 100 pages. I have a copy at home if anybody wants it. I read through this in college. It was like just a book that I picked up in college. And it kind of opened your mind up to the reasoning as to why we can't get to the speed of light. We're not going to go into a ton of that detail. You can take an entire course on relativity. On his book, there's whole courses in college on that one topic. So we're going to talk for now about the fact that there is a finite value of the speed of light that we cannot go beyond. If we could, everything would change. Okay? Everything would change. It'd be like being able to go through what's called a wormhole. In space, we talk about these things called wormholes, and the theory is that you enter a wormhole here and come out over here. Well, how could you travel from here to here in no time? That's time travel. That's teleportation. That's literally what it is. Time travel is moving back in time. But in reality, if you could go through from here to there in no time at all, then you are traveling through time also. Okay, it has to do with exceeding the speed of light. So we did talk about that for a while in the other class, okay? The ideas of it. And that's good. These are good questions about this. But to start us off, I guess, today, let's first talk about what an EM wave is. So in the last few sections, we've talked about transverse waves, longitudinal waves, pulse, periodic. We've done a lot with waves in general. We've talked about the properties, amplitude, frequency, wavelength, all those things. Well, they continue in this section here. Okay, after this section, we're going to move on to electricity. So we're kind of going to be done with waves at the end of this. But electricity also involves EM waves. So we're not really done with it, but we're done with the concept of waves after this. What I want you to see here is that EM waves are different from sound waves. Sound waves were longitudinal. They propagated towards you. An EM wave is actually two transverse waves next to each other, perpendicular to one another. So you have what's called an electric field, and I'll line it with this marker in yellow here. That's the electric field oscillating. And then you have a magnetic field, and that's in blue. Well, if you look at these two, they're at right angles. This one is this way, and this one is this way into the board. So we have this coming out of the gauge like this, or in this direction. This is the oscillating electric field in yellow coming this way. The magnetic field is this way, and those are at right angles to one another. So an EM wave is named according to what it consists of. It consists of an electric field and a magnetic field. Okay, electromagnetic wave. Now, before I get into what they are, we're going to do a lot with that. But I want you to make sure you remember that this is really a combination of two transverse waves. The electric wave and the magnetic wave. Okay? All right. Let's talk about the speed of light for a quick second, even though we already alluded to it. So this is the value. You don't have to write it down. It's in your notes and it's on your formula sheet. But I'm not going to give you this value on a test. It's on your formula sheet. So if you're working with problems that involve EM waves, you should know that they travel at the speed of light. 3 times 10 to the 8 meters per second. So Matei asked the question in the other class. Matei likes to ask a lot of questions. He asked the question in the other class, but he asks really good questions. He does. They're really thought-provoking. He said, well, okay, so you said we can't go beyond the speed of light, right? And I said, yeah, you cannot travel faster than this. He said, well, what if we go from here to China in 2 seconds? What if we had the capacity to do that somehow? And I told him, well, let's see what that value is. So I had him calculate half the circumference of the Earth, right, in meters, and then divide it by 2 seconds. It turned out that to go from here to China in 2 seconds, you would have to travel at 1 times 10 to the 8. So pretty close to the speed of light, a third of it. Okay, a third of the speed of light you'd have to travel to get to that value. Now, can you get to that actual speed? No, you can't. There are limitations. First of all, you're on Earth, so there's friction in the air. If you're in space, it's a different case. If you're in space, theoretically, if you just keep applying force, and F equals ma, you're going to keep accelerating, so eventually in space you would reach the speed of light. You're not going to for other reasons. But on Earth, specifically here, we don't have the capacity and energy to get there. To actually physically accelerate an object enough to change its velocity, to get it up to the speed of light, would take so much energy that we could produce energy for the next hundreds of years and not be able to do it still. Until we're able to get things like fusion energy, fusion or fission, both, but fusion a little bit, you get more energy out of it as a result. And until we're able to actually harness that amount of energy, which to this day we cannot, that's why nuclear reactors are not very popular still. Until that happens, we're never going to come close to getting the speed of light. Even when it does, the object that you'd want to accelerate is probably going to be so massive that because of F equals ma, you would need so much force. Okay, if you have a big spaceship, like think about Star Trek and Star Wars. I'm a big Star Wars fan. I don't know Star Trek, but I've heard the show is awesome. But Star Wars, I know that they try to jump to light speed. That's the whole idea in the movie. To escape like certain ships. What's the Millennium Falcon, right? Yeah. The Millennium Falcon, the one that Han Solo flies, is the one ship that can get to light speed. Now, that's this speed right here. In the movie, they don't talk about how it happens, obviously. Just suddenly out of nowhere, the ship goes from here to like launching into space. And you see it's like gone instantaneously because it's traveling so fast. Now, in that movie, if that were physically able to happen, the amount of energy necessary to move a ship that large would be insane because the mass is so large. So because of F equals ma, if you have a lot of mass, you would need a whole lot of force to accelerate that. And to accelerate it at the speed that he did, or at the rate of acceleration that he did in the movie, would take an insurmountable amount of energy. Something that you cannot even get to or attain. So to give you an idea about some physical limitations as to why we cannot approach this, not just theoretical. Theoretical, you want more explanation on like approaching the speed of light, why it's a finite limit? Seriously, read a little bit more on it. There's a lot more to it than just this. But I'm trying to give you guys some real life explanations as to why this is not even possible for us to get to. We don't have the energy or the capacity to get to that kind of a velocity. Okay? This is a velocity that would take, I forget the number, but it's less than a second. For light to go from New York to California would be less than a second. That's how fast that is. Imagine being in New York and then less than a second later you're in California. That's what it's like to travel at the speed of light. So this is not going to happen anytime soon for some actual massive, particle. This is really the speed for massless particles, or close to massless particles. Something to note is that this is always assumed you're in a vacuum. So the speed of light in space, like when the light from the sun travels toward us, it's traveling at that speed through space. It is. But once it enters the atmosphere, the light gets bent. We call that refraction. We're going to do a lot with diffraction in the next section. But that's where the color of blue comes from. That's why the sky is blue. It has to do with the light slowing down as it passes into our atmosphere. And it refracts or bends at a specific angle. That angle is the angle that blue light would be a result of white light bending. But again, you have to be in a vacuum to get up to the speed. So even if we could physically have the energy to do it, on Earth we couldn't get to this speed because we would eventually reach some sort of velocity that terminates, like some sort of terminal velocity, whether it's horizontally or vertically. Questions, thoughts? A lot of theory here. I know it's a lot of theory and heavy stuff, but what I want you to get from this is that this is a finite value. We cannot exceed this value. Okay, but radio waves, gamma rays, all these rays we're going to talk about in a minute, they travel at this speed. When in a vacuum, they travel at this speed. So let's go ahead and take a look at these types of waves that we're talking about now. So this is the EM spectrum. First of all, what is a spectrum? What is a spectrum? What does that mean? You hear the word spectrum. A field? What do you mean by field? You could use the word field, I guess, but you'd have to give me more explanation to it. A variety. A field of variety. A scale. A range of values from low to top, right? From min to max. So all those words are fine. You could say it's a field of values from a min to a max. It's a variety of values, a scale with all these values, but from a min to a max. So that's what a spectrum is, from one value to another. Anyone have any siblings or family that's autistic? Okay, well, autism is on a spectrum of values. So my mom works with children with autism, and some children are very high functioning, and some are not. So it's a spectrum, meaning you go from students or children or younger folk, for the most part, that she works with, that really can't do much on their own. they're very low functioning autism. And then there's very high functioning autism, and there are people in general that can, that may have a small, maybe on the autistic scale, but are able to interact with society still. So you talk about a spectrum of values. Here, it's the same thing. We go from low values to high values, or high to low. What's happening here, I want you to pick up on though, if you notice, we'll see that we have not only wavelength, lambda, for each of these, but we also have the corresponding frequency. Now, remember your book I told you uses F. This is out of your old text, so these are all Fs. We called these omega in the last chapter, all these values of F there. And what we'll recognize here is that the frequency is very low with radio waves. And what I mean very low, I mean relatively speaking. This is the lowest frequency. And then the frequency at the other end is very high. So what we'll notice is that we have a minimum frequency over here and a maximum frequency over here. From min to max, the frequency increases from radio to gamma. So these waves are categorized by their frequency. That's how they're categorized. If you fall within a certain frequency range, you are an infrared wave. If you fall within another frequency range, maybe you're considered an X-ray. So based on the frequency, the name of the wave changes. And what do you notice? The applications change a lot. We're going to really focus on applications here more than anything, about why this is very useful. That's what we're going to really try and focus on, the applications themselves. Now, what we'll notice, though, since the frequency increases from radio to gamma, the wavelength will do the opposite. The wavelength is a max up here, and the wavelengths are really small down here. Because wavelength and frequency are related how? Wavelength and frequency, how are they related? Inversely. Okay, I hope you knew that one. That was on your test yesterday, right? How are they related? They're related inversely, wavelength and frequency for short. So we talked earlier in the year already about how X-rays are really small in wavelength. We kept saying, they're really small, they have to be able to pass through your body. Well, look at the actual length. We're on the nanoscale. 60 nanometers. That's 60 times 10 to the negative 9. That's what that value is. Whereas radio waves, look how long radio waves are. They're greater than 30 centimeters. They're greater than 30 centimeters is almost around a foot. And when you look at an actual ruler, usually it's around 30 centimeters. Here's 30 centimeters. Radio waves, the smallest radio waves are this big. The smallest. That's literally the length of one cycle. That's how big radio waves are. Now, we're going to see in a moment, we're going to look at the FM span and then the AM span. So when you tune into your radio in the car, you have the AM and the FM. What's happening is there are different levels of wavelengths and frequencies that you're tuning into. So you're adjusting your tuner to receive certain wavelengths or to receive certain frequencies that are traveling toward your vehicle, whatever it is you're in, whether it's a handheld radio or a car. So we have, again, long lengths, small frequency, high frequency. Let's go into the applications of these, and then we'll start talking about visible light for a little bit, because this is the one that we obviously focus on. So applications for some of them are really obvious. Like a radio wave application would be radios. Old TVs that used to have antennas, they use radio waves. Now, do we use radio waves anymore for TVs? We use fiber optic signals for the most part, which travel through cables, a little bit different. Traveling through the air, it's a little bit harder for the radio waves to get to your television, but traveling through the actual cables, that's how we get our television now. These are old TVs. A microwave, besides a microwave itself being useful, right, to heat up food, we're talking about research and then navigation in the air. So radar and then aircraft navigation in general. Infrared. Where have you heard infrared waves be used before? Infrared. Where has that been used for?
Military and laser.
Yeah, military applications is like the first one everybody hears about. Why? Where does it come up in military? Where does infrared play a role?
Night vision.
Yeah, night vision or infrared goggles. Infrared is something that can seek heat signatures. It can show if there's a body physically somewhere. So I talked, I think at one point already about when the U.S. went in to capture, was it Bin Laden, right? When the U.S. went in to capture Bin Laden, and there was in that like the chopper that made no sound and all this stuff. they had dogs that were wearing infrared goggles. They had, obviously, the military wearing it. They could see through the walls to see if there are bodies behind there. They could pick up heat signatures beyond that. Now, those goggles are not just infrared anymore. They do a lot more than just that. But that's just one example of that. Any of you have that FLIR camera? F-L-I-R? If you have it, that would ring a bell. If it doesn't ring a bell, you probably don't. Anyone know what I'm talking about? FLIR? It was popular like a year ago, and I didn't buy it because it was a ripoff. It's like $300. You attach it to your smartphone. It's like $300. You attach your smartphone, and it allows your smartphone to change its camera into an infrared camera. So you could hold it up, and you would see somebody's body. You would see like red in the inside, and as they go outward, it gets cooler. Or if you had like a hot water pipe, if I turn the hot water on up here, and you held the infrared camera like here, right down below, you could literally see the water flowing behind this. It's kind of cool. Yeah, it's really useful, and you could probably find like, all right, where is my water line frozen in the backyard in the winter? If your pipes freeze, you could find where the chunk of ice is by using an infrared camera. Very useful, but for $300, not very reasonable. But they're becoming more consumer available, or more readily available. I'm going to jump over visible for a second. We'll go back to that, because that's what we're going to focus on. So infrared, and then ultraviolet are on other sides of visible. Can anybody hypothesize as to why those are the names? Use your context clues and take a look. Why is this called infrared, and why is this called ultraviolet? Like, these are just arbitrary names. These are arbitrary names. They were invented, somebody came up with them. I don't really care why or who or when. But these make sense. The colors, that's exactly right. Take a look at the visible spectrum here. We'll notice here that red waves have a high wavelength but a very low frequency. Violet rays have a low wavelength but a higher frequency. See how this is a higher frequency than this one is over here? So because of that, let me point with this. Because of the fact that this has a high frequency, this is violet light. Frequency that's above violet is called ultraviolet. That's why this has a higher frequency than this one does. Infra, I-N-F-R-A, means below. So below red in frequency. So the name of this is not arbitrary at all. Infrared means the frequencies are below red, right below red color. Ultraviolet are frequencies of rays that are just above violet. Okay? UV light, you use it sometimes. Some of you, any of you have like this, as another ripoff, really doesn't work well. Toothbrushes with like the UV container, it like shines UV light to like sterilize your toothbrush head. It's like a new thing that I've seen in so many stores now. It's like $40. It's not doing much for you. If you really want to sterilize a medical instrument, you have to put it under a lot of UV rays, a lot of intensity of UV rays. What is it? If you have, if you've all been to the dentist at some point. When you go to the dentist, do they just say like, all right, I'm gonna use this pick on your mouth. I used it on the guy before you, but who cares? Why not? Right? Who cares? Mouth, right? I rinse water on it. That'd bother you, wouldn't it? So what do they do with their instruments? They actually send them away to a company that is only there to sterilize, and then they get them back in a container so they know they're clean. They're not going to replace a metal instrument every time. So they actually undergo UV radiation in order to clean these medical instruments. They're returned, and then they're able to be used again. But they don't just run them under the water and then say, oh yeah, let's just use it in your teeth now. They use this sterilization for these medical instruments. Fluorescence, this is really interesting. If you're interested in forensic science next year and you want to take forensic science, you're going to use UV light to take a look at fluorescence. And fluorescence gives away certain characteristics of materials. For example, the DEA uses it for drugs. Certain drugs fluoresce under certain lights. So if they want to see if something is actually real on the spot, you'll see anyone that's a forensic analyst, they're not only carrying around like tools, calculators and stuff to calculate things, they carry around usually some sort of a UV light. They'll shine UV light on things. You ever see like, a crime scene, they shine like a UV light and they see, oh my gosh, there was so much blood here. Somebody cleaned it up and you can see it with the light. I don't even know if that one is actually true. It probably is if they're showing it on TV because they probably don't want to lie too much. But UV light is something that shows minerals that fluoresce, that have any sort of fluorescence in them. X-rays we talked about already for just medical examinations in general. It's also used for cancer treatment. But gamma rays are also used for cancer treatment. Gamma rays are interesting. What I like to point out for gamma rays is the first part. Imagine you are in like the Roman era, Roman and Greek era, where they had big, what was it called? What's the one with the columns on front? Is that called the Pantheon, or it started with a P? I thought. The Greeks or the Romans built the one that has all the columns. Parthenon. Thank you, Mike. So if you look at one of those today, you're probably pretty confident in the fact that it's not going to collapse on itself. Now, hundreds of years ago, how did they know that there wasn't a little crack in the concrete that might propagate and spread and cause a weak point or a failure point, and then the whole thing comes tumbling down? Well, they weren't able to. Okay, they were not. But nowadays, we can actually use gamma rays to identify any sort of structural flaw in a material that's inside of the material. So for example, imagine a concrete column with a diameter of like 3 feet. How are you going to know if there's a crack on the inside? You can't open it up, or else you're going to create a break, right? You're going to create a crack to see the inside. So how could you physically see if there's a problem? Well, gamma rays are actually used. Again, the size of the waves are what's important here. The size. The waves are tiny. They're able to actually penetrate this material as a result. If you took a radio wave and tried to broadcast a radio wave at a concrete column, it's not even going to pass through it. It's going to go around and it'll get reflected by it. It'll cause some sort of interference. Whereas gamma rays are going to pass right through. Well, the way that they pass through, the rate at which they come out of there, can identify if there are some sort of a small crack in the middle that might continue to spread. Okay? And then the last one is food irradiation. Okay, so to get rid of radiation that might be caused due to like pesticides and stuff, they use gamma rays for that. So let's focus on visible light for a second. Okay, let's focus on visible light right here for a little bit. So first, the visible spectrum, you know this one, you learned this as a kid, Roy G. Biv, that was the way you memorized it. Red, orange, yellow, green, blue, indigo, violet. Indigo is really not even a color, I'm sorry, it's ridiculous. It's between blue and violet. It was out a long time ago. It's not even shown in this diagram here. Okay, Roy G. Biv was the acronym, so it remained that way, but the indigo doesn't even show up. But it's a spectrum between there. But what's different is that this is the lowest frequency, this is the highest frequency. Materials absorb colors. They actually absorb all the colors that you don't see. So when you see this pen, the case is blue, you're literally seeing blue light reflected off of this surface. Where did all the other colors of the light go? They're absorbed by the material. So this plant here absorbs red, orange, yellow, blue, and violet. But green gets reflected because the leaf is physically green. So what are you seeing in visible light? You're seeing the reflection of only one of those colors or one of those frequencies, which is why you see blue in the sky. All you're seeing is the refraction in that case of blue light as a result of white being bent.
Why do you say like things don't have colors in the dark? Because there's no light?
That's exactly right. Yep. Think about in the dark. Why do you see everything black? Because is there any light? There's nothing. So if you think about it, this desk looks black to me, doesn't it? So what's happening? Is it reflecting all the light or absorbing all the light? It's absorbing all the light. That makes sense. Now that Angie asked the question. That was one of my follow-ups. If you've ever been to the beach in the summer, do you ever wear a black shirt? No. You know as a kid, your parents know better. If you wear a black shirt, it gets hot really quick. When I was a kid, my dad built us a basketball court in the backyard, and he used asphalt, just like a blacktop, you would use for a driveway to make the court. The only problem was in the summer, what happened? It was hot as anything. And in the summer, I had a couple of brothers who always liked to play basketball. We were playing barefoot all the time in the backyard. You have the grass, we had a pool and the basketball court. We'd get on the court and you would burn their feet. You'd have to spray it down with water just to cool it because the color of it would absorb all of the light, all of the visible light from the spectrum. When everything gets returned to you, you see this color right here. You see white. Okay, that's the combination of all of these different colors getting reflected back toward you. Same goes for at the beach, besides the color of your shirt, but the color of the sand. If you've ever burnt your feet on the sand at the beach, you're probably walking over it looks like violet-colored, purple-colored sand, and that's always the hottest sand at the beach. It's because of the color of it. Not Not just because of the color. The color changes as a function of heat also. But you'll see the color of the change. If you find like plain, perfectly white sand, it'll most likely be pretty cool, the temperature of it. So let's also talk real quick about the fact that we see a very small portion of the EM spectrum. And let me give you a little illustration. I tried to find, there's a really good illustration of this. I found it in the other, class. Let's see. EM, but I wanted to find one with sound also. Let's search for that. XKCD is a very math, science-oriented comic site. Every day the guy puts up a new comic, and it's actually really kind of cool. And they're always, I call them funny. They're witty. Okay, they're witty. So let's look at this first one to show you an idea of what I'm talking about. So here's the EM spectrum along the bottom. Here's wavelength. Here's frequency. Let me point so I can have the pointer. Here's wavelength. Here's frequency right here. We see what we use them for. Telephone, radio, microwaves, toasters. Is that what this is? Toasters. Infrared. Well, here's the UV. Here's the visible spectrum right there. Look how small it is. That's the visible spectrum. That little bit right there. Everything outside of there we cannot even see. The human naked eye can only see this tiny little bandwidth right here. What's really interesting is I couldn't find the other comic. The other one I like better. It puts the x-axis as the EM waves, and then on the y-axis it puts sound as a function of frequency. And if you know about sound a little bit, you know that you can't really hear all the sound that exists. How many of you have a dog? All right. How many of you have a dog whistle? Interesting. When you blow that whistle, do you hear anything?
No,
The dog does. The dog perks up. By the way, try to be nice with the dog. That whistle is like nails across a chalkboard to you, just so you know. So the whistle is at such a frequency that the dog can hear it, but you cannot. Listen, what's up?
Why is there, that sound that only like people under 25 can hear?
Yeah, you guys are like reading my mind today. So in the other class, I actually brought this up. There was an app for a while, like 5 years ago, when I taught another school that the kids would mess with me with. And it was what we were talking about in class. You can sit there and change the frequency. And you guys will all hear like a high-pitched noise, like that. But I wouldn't hear it. As you get older, the frequency that you can hear decreases. So when you get hearing aids as an adult, it's not just because you can't hear, it's not loud enough. It helps that too. It amplifies the sound. But it also helps to increase the range of frequencies that you can hear. So as you get older, that range of frequencies decreases more and more and more. So suddenly you can't hear these high-pitched sounds when others can. So I remember specifically when other students they were like, somebody was like going like, what is that noise? And I had this one kid in my class who was like a little like computer freak. Like he knew everything about computers. And he was the one who had it on his phone. He had it out and he was doing it and just messing with it. But I didn't know what was going on because I didn't hear it. And like a couple of them were like going like this. I'm like, what are you guys doing? And he's got this smirk on his face. And he holds it up to me and I see it as a certain frequency and hertz. And I'm like, I see what you're doing. And I realized he was actually sending out this really loud sound that nobody could hear, really high-pitched frequency that I couldn't hear, but all the other students were getting affected by. So the other, I heard something, so I don't know if that was somebody doing that, messing around. If you can find an app for that actually does that, try it. We could try it right now. It's fun. But the other one, so the other image, the comic that I cannot find or get a hold of, along the y-axis, shows the range of frequencies that are possible for sound. We hear only a tiny little bandwidth, and we see only a tiny little bit. So in reality, this is what humans can perceive. This little piece of the entire puzzle, whatever, the entire graph. We hear a tiny bit of the frequency spectrum. We see a tiny bit of the EM spectrum for light. We literally only have a little bit.
Oh my god, that's so long.
Is somebody doing it right now? Who's got it? Lucinda? Can you change it? Can you lower the frequency instead of higher?
It's a video. This is it.
I'm still not hearing anything.
No, it's
Okay. Well, the one that he had was an app you could alter the frequency and sit there and use a slider.
Yeah.
So as you changed it, like certain people could then suddenly start hearing it.
Actually,
Are you doing it still or no?
No.
Okay.
Wait, so what's this? There's one people were talking about. Oh, I heard it.
Oh, that's really loud. You don't hear that? No.
Literally nothing. Nothing. I'm not joking. I'm not messing with you guys at all. Like you sit there, I won't even look, and you could turn it on and off. I would not hear a difference at all. There's no difference. Still on or is it off now? All right. Eventually turn it off, please, so people don't get headaches. Say again? Yeah. So if you know anything about biology, there are certain, specifically insects, that have different cones and receptors in their eyes that allow them to see differently. So like bees see blue and yellow. That's like the two colors that they only see. They can't perceive the other primary colors at all. What is it? Dogs. Okay, there you go. Blue and green. If you're colorblind, we'll talk about color. Actually, let's wait till the next slide to talk about color blindness. Let's go to the next slide. Let's talk about why color blindness is involved with red and green a lot. Red, green, and blue are the primary colors for light. I'm not talking about art now. So for those in art, it's different, right? You have different primary colors for art. There are different pigments, right? What are the colors for art? Yeah, I don't think they're the same. Red, blue, and yellow. Okay, red, blue, and yellow. So here, if you think about, how many of you ever had like a 6-foot hero delivered at a party? It's wrapped in cellophane. It's like a translucent, like color material. Cellophane is like wrapping paper that you can see through. It's like red or green or whatever. That's what this is showing you here. So if you had a red filter, and then you took a green filter and put it over that, what color would come through? Yellow. It's the combination of those two. If you wanted to get some sort of a teal or turquoise, it's this green and blue. Pink is red and blue here. If you want white light and you have a flashlight and you put all three of these filters one over the other, I got to get some of these filters. Maybe I'll order some of them. You put them all over each other, the white light will pass right through and you won't even see a difference. It's the combination of these primary colors that create all the other colors. Now, in your eyes, you have cones. Your cones are like receivers of light. If you're missing one of the cones are red, green, and blue. Same three here. If you're missing one of those cones, it's not like you mix them up. So many people have a misperception that color blindness means that you switch red and green. I don't know where that came from a long time ago. It's not the case. The difference is this. You can't tell the difference between red and green because you don't have the cone to pick up on it. So if you don't have, for example, the green cone in your eye or something's wrong with that, you will see red and green as almost the same thing. They'll both be like shades. They'll be shades of the color that they actually are. So if you've ever seen in bio class, I don't know if Ms. Myers does this, but the test to see if you're colorblind right off the bat is you take like a box that's colored in green and you write something in red inside of the box. And you ask students like, who only sees one box? And if somebody raises their hand, they're colorblind for sure. Because they're not picking up on the other color inside. They don't see the difference between the two. Now, these are also, how many of you before have ever toggled with your TV settings? In your TV settings, the pixels, these three colors right here. Every pixel can either be red, green, or blue. It's a combination of those three and intensity levels that causes the different colors that you're actually seeing on the screen. But these are the three primary colors. Now, I know that's the way for cathode ray TVs, like regular TVs. I wonder now, I don't know what are TVs called now? LED, is that what they're called now? It was plasma, then LCD, is it LED now? Yeah. LED has to do with the light bulb that backlights. But I don't know if those TVs work on these three, but I'm pretty sure they still do. I'm pretty sure if you change your video settings in the TV, you'll have levels of blue, levels of green, levels of red that you can adjust on like a sliding scale. Is that right? So when you're on the TV, you can choose that color. There we go. See, that's something interesting I didn't know. So, but these three colors are the three primary that your cones of your eyes also work around. Let's finish with this example for the day. So, if we look at the FM spectrum, the FM radio spectrum here, if you've ever tuned in the car, you can't go below around 88, right? 87.5 to be exact. And your tuner can't really go above like 107 point something. It's 108 actually. So the FM band, or the FM spectrum, ranges of frequencies from 87.5 to 108 megahertz. So the smallest frequency is 87.5. Mega means times 10 to the 6 hertz. The largest frequency available from the FM radio waves is 108 megahertz. So that's the min and the max, meaning FM waves are somewhere between that. Okay, somewhere between that. Now, the question that we're asking this is, what are the lengths of the shortest and longest radio waves themselves? Well, if I think about the relationship, how are wavelength and frequency related? Wavelength and frequency, how are they related? You answered it before. Inversely or directly. That's one of the others. Indirect or direct. They're inversely related. So if I want the largest wavelength, that will probably correspond to smallest or lowest frequency. So in this problem, we're asked to find the longest and shortest wavelengths. So really, we have to do this problem twice. Okay, and we have to use our formula. Here's our formula from last chapter. Again, I told you this is going to carry over. The last chapter is related. Here's our formula, but what's V now? It's not given in the problem. I don't have a velocity.
Speed of light.
Good, speed of light. It's the speed of light. All EM waves travel at the speed of light. So there's our formula for lambda if I solve for lambda. The wavelength is the speed over the frequency. So if I want to do this twice, I can take the value of the speed of light, divide it by, let's start with the min. We'll start with the minimum frequency. That'll give me the longest wavelength. And then to get the shortest wavelength, I'll take the higher frequency, and still again, the speed of light. This will end up being 3 points, unless somebody has it, 3.4. And the other one? 2.8. Now, before I let you go and the bell rings, please hold off for a second before you even move. Look at these values. I told you a little while ago that radio waves are at least 30 centimeters. Well, this is 2.8 meters. That's 2 of these sticks. So it looks like the shortest FM waves are 2.5 or 2.8 meter lengths, but we just said that radio waves can be only 30 centimeters. Where's the missing part? Why is it jumping from 30 centimeters to 280 centimeters? What are we concerned with in this problem? What spectrum? What band? What band are we looking at here? Radio, but specifically, which band? Which one? In the problem. Read the first sentence of the problem. We're looking at the what band? What's FM mean? Figure it out over the weekend. Think about this. Okay? You have FM and you have AM. Try to think about that. Okay, you have FM and you have AM. This term reflection you've heard before. When you hear about reflection, what do you think? What's the first thing to think about for reflection? Mirror. Okay, it's the easiest and the most fundamental thing to think about is a mirror. A mirror gives you your reflection. Why does a mirror give you a reflection? Why does a mirror give you your reflection? What is a mirror? How about that? Let's start with that first. What's a mirror?
It's a plate of silver or something, and then it has glass over.
Yep, and that silver has to be polished really nice, right? So the idea is that you're going to have a surface that is extremely, we're going to use the word in a minute, we're going to call it specular. Specular is a very smooth surface. So a reflection comes about from some sort of redirection of your EM wave. And from the last class when we started this lesson, we talked about the fact that we have light waves all around us traveling from the sun. It's a type of EM wave. Well, the light wave actually gets reflected, and you see your reflection in the mirror itself. So when we're talking about reflection, that's the easiest way to think about it. Now, the easiest way to visualize it, the easiest way to visualize something like this would be to think about a game of pool. How many have played pool before? At some point in your life? All right. So in a game of pool, if you strike one of the other pool balls with the cue ball, the ball will hit the bumper and usually rebound off the bumper at the same angle that it hits. So for example, let's say these are the pockets on a pool table. The ball is here, and it's struck in a way that it hits this. Well, if it hits the bumper at that angle, call this theta, it's going to rebound at the exact same angle, theta. So reflection, when we think about reflection, think about a pool ball hitting the wall coming back. That's the same thing as reflection, really. It's an EM wave hitting a surface and rebounding. When you want to use radar, what happens? What happens when you use radar? How does it work? The idea of reflection comes into play. Mike?
Sound waves.
How about just waves?
Radio waves bounce off the object, bounce back.
Yeah, and it tells you exactly where the object is based on how long. We did this earlier in the year, obviously, right? Remember the motion detector? The motion detector was exactly that. It was a reflection of a wave that was being sent. We called it a pulse. Now, you remember the word pulse now from last chapter. It kind of makes sense. A pulse was a wave that was sent independently. It wasn't like it was a wave continuously being fired. It was quick pulses that were being sent. So here, when we look at reflection, I want you to think about a game of pool. That incoming angle equals that outgoing angle. So let's see that with a diagram now. We have two types of surfaces, and I already alluded to this word here. The word that we're looking for perfect reflection is called specular. Specular. And the easiest way to remember it, what are glasses called? What did you used to call them? Spectacles. Okay? Now, glasses do not necessarily reflect light. They actually bend light a little bit. Okay, but it's related to light, so it helps students remember that word. Or just remember the word specular. Diffuse. What do you think when you hear diffuse? You hear the word diffuse, what do you think of? Say again?
Things spreading out.
Spreading out, coming apart. Mike? Anything to add? You got a hand up too. No? Okay. So what I think, go ahead.
Like it crosses the barrier?
Crosses the barrier, think of diffusion, right? Yeah, from your bio and chem class, you have diffusion, or you have osmosis, all those types of diffusion. Yeah, when you think of diffuse, think of something almost like spreading out or dispersing in separate, in arbitrary directions. That's what's happening here. The light rays, the EM waves, come from the sun. The sun provides these waves of light. They come in somewhat parallel fashion. So you're seeing here that it's actually denoted that these are all parallel. Okay, see, these are all parallel here. Now, when it reflects off a specular surface, the outgoing rays are also parallel because they go out at the same angle they came in when it's a smooth surface like a mirror. Now, when it's not a smooth surface, for example, this desk would be considered diffuse. It is reflecting stuff, actually. There's a slight bit of reflection, even though the color is black, and we talked about how that absorbs all the colors. There is something being reflected, and you can see it. If you just change your angle on the desk, you'll see how the light changes. Literally, just go like that, and you'll see the light changing on the desk. That's a diffuse surface. You cannot put your face over this and see it. What's an example of a specular surface outside of a mirror? Outside of a mirror, what are some specular surfaces? Give me some examples. Water? Give me more specific. Good. Still water. Very good. A flat pond is a very good example for one. And you always see photographers take a picture first thing in the morning, if they're like on a lake. They go out and the lake is perfectly still, and they get a picture, and the trees are perfectly mirrored in the lake. Have you seen this before, where you can literally see the trees in the lake? Because it's a perfectly still surface, it is almost perfectly specular at that point. If you drop a single rock in there, it'll start to create ripples, and you would see that. It would affect the picture. What's another example? Another example. A spoon. Good. Anything that's what? Let's get a general statement. Use the word spoon, but what's a spoon made out of?
Metal.
Yeah, anything that's polished metal. Polished metal. God bless you. You're welcome. Thank you. Okay. So, I mean, he's one person, right? I always say it. So polished metal in general, polished metal gives you your reflection. That's why a mirror is polished metal with glass over it. That's all a mirror actually is. I'm trying to think of another example I had. Oh, another example in the other class somebody gave was your iPad. Click your iPad off for a quick second, you can see your reflection in it. It's because the smoothness of the actual glass and what's behind that glass, some sort of a metal material. It's a little dark, right, the reflection, when you actually look at it, but it actually does give you a reflection. So this is a relative term. Is that clear what I'm saying by relative? What do I mean when I say it's a relative term? Specular and diffuse. Why is it a relative term? What does it mean by relative? What do I mean by that? Like if I said, if I'm like, I'm pretty good at, I don't know, I'm not good at pool. I'm decent. I say I'm pretty good at pool relative to my brother, but not relative to Mr. Hall, who plays a lot of pool. What does it mean when I say relative? Yeah, it's dependent or compared to. Dependent on the other or compared to the other. So these phrases are really relative phrases, okay? So something could be specular to you because you see a reflection in it. But when I was in engineering, we did a lab on what was called surface quality. And believe it or not, something even like a piece of metal that you think is nice and shiny and you can see reflection may not be very smooth. At a microscopic level, there are a lot of ridges there. So in this lab, we had to actually learn how to polish metal with a machine. And then using a microscope, look at the actual peaks and measure the heights to see how actually smooth it was. So it's a relative term. You follow what I'm saying? So if you're on an everyday basis looking at a mirror, sure, that's considered specular. But if you're somebody who's working in science all the time and you need to be a perfect barrier, that might not be considered specular compared to what their values would be for something that's specular as far as the smoothness of the surface. This is what I was speaking about earlier. Think about pool, please. The incoming angle. Let's write a little label down here, please. This is called the angle of incidence. I call it theta I. Give it a little subscript, even though your book doesn't give a subscript here. This is an image out of your book. Call it theta I for the incident angle. Now, the angle of reflection, leave it what it's called. We call that theta prime, or theta with an apostrophe. The reason it's not called theta R is because R is going to stand for what's called refraction. And we're going to study refraction in about maybe a minute or two. Okay, we're going to start refraction. This is reflection. So whenever you're thinking about reflection, the incoming angle equals the outgoing angle. Now, what do you recognize about this diagram that's a little bit different? How are we measuring theta in this diagram that's different from the past? How are we measuring theta?
It's on the y-axis.
Yeah, it's with respect to the y-axis. Very good. So the angle of the light that's coming in is denoted by the actual ray and the vertical, or we call this the normal. Okay, remember normal force? Remember normal force? Normal force was perpendicular to the surface. Well, take a look. Here's the surface. Isn't this line perpendicular to the surface? That's why it's called the normal. Again, it's called the normal. Normal means perpendicular. It's called the normal, it means perpendicular. So the angle that you're measuring is with respect to the normal itself. Okay, let's stop here for this one. We're going to go right to the next lesson, but you have some homework here. Not difficult homework, decent amount of questions, but not very difficult at all. Okay, stuff that's going to be very straightforward. The only formula we used in this whole section really was this one earlier, which we used in a previous section. That was the only actual formula we used here. Besides that, everything else is really theory. Okay, everything else was theory.
I just had a question about
Yeah.
tomorrow. Is it only those problems, or is it the ones on the other slides as well?
Yeah, so we're going to see how far we get, but I think we'll get through the rest of the next slides in the other class. This next lecture is only like a 20-minute lecture, so we should be able to get through it. The next lesson has, I think, 2 or 3 homework problems.
3.
3? Yeah, so it'd be about, you're looking at like 7 or 8 homework. What is that? Yeah, 7 and 3, 10 total. Yeah, I think it'll be all right for one day. You'll make it.